Hello, everybody. So I was at this tech conference the other day, and I was part of the audience. And the last speaker came on stage right around this time, 5 o'clock, right? And the audience who were quiet till that time, suddenly there was a buzz in them. Everybody was sitting up and like really focused and very excited. So I asked the guy next to me, hey, what's happening? What's the big deal about this guy on stage? He said, no, they're not excited about the guy. This is the last session before the happy hour. They are excited about the happy hour. So I understand that you're not very enthusiastic, not because of me, because there is no happy hour, right? So what? No, I'm just kidding. The topic is how large language models work. Honestly, how large language models actually work, I have no idea. And neither does anybody else. And this is something I want to actually put it out there. Nobody really knows how a billion or so parameters adjust themselves so as to make things work or make LLMs make, no one knows why they work the way they do. So what we'll do today is try and create some kind of intuition, a kind of analogy that kind of explains or tries to explain this beast of large language models. So what we're going to do is we're going to go through some basic stuff that is the bread and butter of machine learning. Neural networks, we'll look at vectors, and then we'll get into large language models. In large language models, we'll look at what is attention layer and multi-level perception, right? So be with me on this. What do you think this is? This is a smart vending machine. Assume I have a vending machine that can dispense drinks based on the time of the day, the weather, my energy level, and whether I am alone or with my friends, right? And so it's going to give me one of coffee, beer, soda, or water. So we're going to try and see how is it a machine like this works, and in that process try and make sense of a neural network. So one thing the machine needs is, it needs me to feed a lot of data into it. And what the data is going to say, I'm going to give it these 4 inputs. I'm going to say 8 a.m., I have high energy, the weather is cold, I'm by myself, I'm going to drink coffee. That's one example I'm going to give. I'm going to give a lot more examples like that. I'm going to say it's 8 p.m., hot weather, energy is low, I'm with my friends, I want a beer, and so on and so forth. So the first thing that you have to give the machine is a lot of data so that it can identify a pattern. And based on the pattern that you give it, right, the network, I'm going to call it the network, but it's actually the vending machine, it's going to learn. It's going to learn how is it that I want my drinks based on those 4 inputs, and then it's going to make a prediction, or it's going to actually dispense a drink for a new condition or a new set of inputs that I give it. So it learns and then gives me an output, right? So this is how we can think of a system like this. Assume there are multiple layers in the system, right? The first layer is trying to do basic association between the inputs, right? It's going to say it's, I have high energy, it's morning time, I'm going to go for coffee, for example. The second layer, assume, it's going to be a little more nuanced. It's going to look at cases like, okay, he's alone, he just woke up, right? So his energy level is whatever it is. And then, how is it going to work with multiple inputs, right? So if you have social setting, if you have time of the day, and if you have weather, how do all 3 interplay? So with each layer, there is a kind of hierarchical learning. So what the first layer learns, the second layer takes that learning from the first layer and adds on to it, right? So that is why it's called hierarchical learning, right? So once I pass these inputs in, it's going to give me one of soda, beer, coffee, or water. If anybody has any questions, please feel to stop me anytime. All right? Okay, now, the way the network understands is, or adjusts things, is what is called weights. So think of weights as importance that the network gives to any of the inputs, right? So if you have time coming in, and if you have weather coming in, what the machine does is, it assigns a weight. Think of weight as a number, any random number that you assign to the input. And that number can be thought of as the importance that you give this particular input. For example, if I were to say the weight I assign time is 2, and the weight that I assign weather is 1, that means I think that time is 2 times more important than weather, right? Now, it's not 2 and 1. It's usually a bunch of numbers, bunch of random numbers, right? And weights, what happens is you set them randomly, and then based on the patterns, those numbers or those weights get adjusted. And once they get adjusted, right, then the weights that the system learns becomes what is called the knowledge of that system, right? That is where I said the brawn becomes the brain, right? So you have the system, it's almost like it's working out or training, and then that weights that it learns, basically the set of parameters, that becomes the brain or the knowledge that the system has. Why is it called knowledge? Because that is what the system uses, or the vending machine uses, when I give it a new set of inputs. When I give it an input that it has never seen. Let's say midnight, I wake up, I am with friends, what do I want to drink? Assume that the system has no idea, has not been trained earlier on that new input, but it's learned a pattern. So when I say it's learned a pattern, what it's learned is weights. Weights are the parameters that you set that make it unique so that it can predict any new scenario or a new situation. Right? So this is just an example, right? In the earlier figure here, right, we said that there are multiple layers. Assume that every layer has a processing unit. We call it neurons. Now the whole thing with neural networks is, initially it was thought to model the brain. The brain has neural nerves and neural neurons that are connected by synapses. So neural networks were based on that ideology that you have multiple nodes. Think of nodes as processing units. Like a thing doing a certain thing. Like one node may be just looking for weather. The other node may be just be looking for social connections, right? And these connections that you see are the weights, right? Now, why they're called weights is this one, right? So you see, what you have up there is the time coming in, right? So the first thing also that I did not explicitly mention earlier is, everything has to be in number format. The input that you give it, right? We said time. So the input that I am assuming is it's either morning or evening, right? I'm going to say that anything over 0.5, I'm just going to say it's going to be evening, and less than 0.5 is going to be morning. So everything has to be converted into a numerical format, because this machine, like a neural network, understands numbers, only numbers. And that is how it works. That is how it works with the weights. That is how it comes up with predictions, right? So everything has to be numbered. So the numbers that you see here for the time, right? So these are the 0.8 for the time, 0.4 for the weather, 0.6 for social setting, and 0.2 for 0.2 for the social setting, right? So these are numbers set such that they form a certain pattern. So in the sense, if you say that 0.2 is me being alone for one input, you cannot say 0.8 is being alone for another input. They have to be consistent. So you have to, first of all, come up with a pattern and say, hey, how do I define these inputs as numbers? Right? How do I define these numbers how do I define these inputs as numbers? And that pattern has to be consistent. You cannot change it across, right? So my assumption is anything under 0.5 is me being alone, right? Oh, sorry, I missed the 0.2 is actually energy level, and 0.6 is the social. So, but either way, you decide on being alone as less than 0.5, being with friends as more than 0.5, but it has to be consistent, right? Now, the connections that you saw are the weights. So what's happening is, as soon as these numbers come in, which is basically the inputs, what the network does is it assigns weights to these connections, and then what it does is it multiplies the inputs with the weights. So when it does the multiplication, what it's trying to do is trying to say, oh, this is the weight that I'm applying, or this is the importance that I give to this particular input. It doesn't know if that is the right importance to give it, but it's going to go with a random value, right? And then it's going to adjust it and adjust it and adjust it till it finds the optimum weight per node that will work as a generalized weight, which will work for any input. Right? I'll come back to this later. Right? So this is what I was saying. So we spoke about the inputs. The inputs have to be numbers. Similarly, the outputs also have to be numbers, because the machine, this numerical machine, does not understand anything outside of numbers. Everything has to be in number format. Right? So the way this is done is you have 4 outputs. This is called one hot encoding. What that does is you assign, so you have 4 places, right? So you just say soda is 1, 0, 0, 0, water is 0, 1, 0, 0. Basically, whatever, you pick a place in this array of 4. Pick one place, right? And you fix that. So soda is always going to be the first number. The one on the left, you see where it says 1, 0, 0? Soda is always going to be that first number, right? And water is going to be the second. You basically allocate a space or a position for the output that you expect. And that is fixed. That means when you get an output from the machine, the first position that you talk about is always going to be about soda. The second position is always about water. Third is about coffee, and fourth about beer, right? Now, because it's a numerical system, right? We said this is a numeral system, right? You give it a bunch of numbers as inputs. And then what would you say? We put a bunch of numbers as weights, multiply them, they go through a bunch of other processes. What it spits out is also numbers, because that's what you gave as input, right? Now, to make sense of the outputs as numbers, they're just random numbers, right? So we just call them logits. You don't have to worry about the nomenclature and all that, right? What you get output is, see, the output of that system is 0.7, 0.2, 0.05, 005. That makes no sense by itself. So what the system does is, it takes that and makes that into a percentage. The formal way is called softmax, but basically what it does is, it adds it all together, right, and then divides it by the total. So what you're basically doing is, you're trying to find what percentage of the whole, the total sum is each of those numbers, right? So then you come up with 0.6, 3, 2, 4, 6, and 7. Basically that means that if you get an output as 0.7, 2, 0.05, and 0.5, what you're saying is there's a 63% chance that this is coffee. Why is it 63% chance? Because you see that position there, 63%, that is position 1, which we said, oh sorry, not coffee, soda, my bad, right? Position 1 is soda, right? So it gets a list of these random, think of them as random numbers, but because you can only have 4, it takes it together, makes a percentage off of it, and then says, this is what I think the output is supposed to be, the soda, right? Now, what we also have is, so you see this line where it says predict, it goes through the machine, right? It takes an output, right? Now, the output that it said it's going to be a soda, right? But let's assume for that same input that I passed it through, let's say morning, low energy, alone, cold weather, right? My answer is going to be, I want coffee. That is the answer that I know I expected, right? But what did we do? We already have that, we already passed that through the system as a feed. We already fed it into the system, right? And the reason we feed it into the system is, when we give it the same set of inputs that I give it and say this is the expected coffee as output, that same input, when I feed it to the system, the first thing the system does is it assigns random weights, right? Because it doesn't know what is the right weight, right? It assigns it randomly. When it assigns randomly, what's most likely going to happen is it's going to say, oh, morning low energy, alone, cold weather, I think you need a soda. That's what it's going to say. But then what it's going to do is, at the second step, it's going to look at the expected coffee that I told it is what I expected, right? It's going to compare the soda and the coffee and say, oh, there is a difference. There is a difference. I did something wrong. I need to adjust my weights, right? That's what happens. This is a step called back propagation. So what it does is, it takes the output, it knows it's erroneous, and because you have these multiple layers that you spoke about, and each layer has weights, it back propagates the error across these layers from the back. And then it...
Sorry, quick question. Still not understanding where the 63% comes from.
Yes, yes.
Was that randomly generated, and then it made a guess that it's going to be this actual output, and then there was an error, so then it's going to assign the 63%? Because the 63% is going to be, I just want to make sure I understand this. I'm trying to answer your question. That's soda, right?
The 63%?
Yeah.
Yeah, so I'm just saying, let's assume that you get this output of 0.7, 0.2, 0.05, 05. Let's assume that's the output, right? And it reads that output randomly assigning it. It just assigned a bunch of weights, right? So, okay, let me just go back.
So that's just like sort of just like randomly assigned
Yes.
based on the percentages?
Yes, yes. Let me just go back to this layer. So you see this layer, right? So the input layer has the points and all that we are clear of, right? The input layer has that. Each connection has a weight. That also we are clear about, right? So each layer has a bunch of connections which are actual weights. So every layer has a bunch of weights that it toys with. It assigns weights, right? And then what it does is it passes it through these layers, right? And as output, it gets this number, 0.7, 0.2, 005, 005, right? Now, there is a few more operations that happen in between. I'll come to that as the next slide, right? But what I wanted to say is we get this as an output because we gave it as the input that we give it is also numbers, right? The input we gave it is a bunch of numbers. The weights we assign are numbers. So it's just going to do a bunch of calculations like this one. This one. You see where it says dot product? 0.8 into 0.7 plus whatever that is, right? It just does the multiplication, adds it all together, and it spits out a number. That's what it does.
The number with the scale there, is that from the back propagation?
Oh, no, thank you. Sorry, thanks for bringing it up. That's the bias, right? So there is also a bias term, right? The reason we use bias is that you want to add some kind of scalability or some kind of flexibility in your models, right? Because it is not always, it's not always a thing that when I am alone and I wake up in the morning, I want coffee. There could be some cases where I don't do that, right? So the reason we have biases to make that flexible adjustment, to make for one-off cases or rarities or oddities, right? And that is also the reason why, in order to make, using four inputs, in order to make one output prediction, we have how many nodes? We have around 48 weights in this layer, right? You see, every connection is a weight. The reason we have so many is it gives us a flexibility to change, adjust, modify one or many till we reach a generalization that tells us, okay, this is going to work for most of the cases that I can think of. So it just gives it a lot of flexibility. Okay, so this part, I think we went to this part, right? Okay, and I just want to show this animation real quick, which is, okay, so this is basically what happens. So you have those 4 nodes as inputs, right? You see those numbers 0.8, whatever that is, right? Just a bunch of inputs that are coming in, right? So it is 8 a.m., sunny, high energy, I'm by myself, right? So this is basically the network, or the vending machine, if you may, right? So you see that those numbers, the soda, beer, coffee, and water, those are fixed positions, because we always know that 1 is going to be soda, 2 is going to be beer, so forth, right? Okay, so this is where it assigns the weights, right? So what you see on top right, that matrix, that is basically the weights for the first layer.
And then that question there?
Yeah.
And then these numbers are randomly generated?
These are randomly generated for the first time.
Okay.
For the first time, it's randomly generated, right? So you see, if you count the number of lines, 4 by 4, 16 lines, that is the size of the matrix up, that box with the weights, right? I'm just randomly assigning it. Don't worry about the number and the weights and all that.
Okay.
This is just random, right? Oops. Okay, so it's assigning the weights. Sorry, I had to replay that. Okay. Okay, let me just pause here. So, when, probably have to go back. Okay, so one thing I kind of missed to mention is, if you notice when the weights become active, I can't forward it, I'm sorry. Something going on. Anyways, so once you assign the weights, you see these nodes that are there, only 2 of them light up, right? So what also happens along with assigning weights is, once you assign weights, right, there is, in these nodes, if you may, those processing units, what happens is, so we saw that it output a number, right? You multiply the weights by the inputs and you add them all together, you get a number, right? Now, along with that, what also happens is, you have something called an activation function. What that means is, you decide whether that node is active or not going forward. So what that is doing is, it gives you an output weight, but then it will decide whether you need to have the node active or not. What that technically means is whether the weight you assign at the first layer, whether you really want to use that going forward. Right? So think of it as bulbs acting up, right? So you see those two nodes in between, they don't light up. That means whatever weights you assigned, those lines connecting those 2 nodes, you're not using that forward. You're saying, I don't want to use this. And that happens because of the weights you assigned, right? So the activation function we usually use is this, right? If it's a number greater than, if there's a number greater than 0, pass it as is. But if it's less than 0, so weights can be negative also. So when you assign negative weights and the sum of those weights, they don't go over 0, you could decide and say, okay, that means I'm saying that the weights you assigned are not significant enough to be moved forward, or in other words, this node will not be active and will not be used going forward. Right?
Does not used mean convert to 0, or?
Yeah, basically what happens is, nothing is going to be output from that node. So that's why it's blank. Right? So even you don't, so whatever you assign, the weights get assigned, but because the output of that node is 0, basically you're not using that node in your calculation. Again, this is by randomly assigning it. Right? We'll see what happens when you come back and say, I need to learn something, or do I need to adjust it, right? Okay, so this is the last layer. Okay. Let me just stop right there. You see that? That lights up beer. That is the same example we saw earlier. You go through this whole process and finally I'm saying, okay, I'm predicting a beer. Right? Then what happens is, this is where it calculates the error. It says, I have a beer because it's running through the randomness. But then it knows that it's supposed to be a coffee. Why does it know it's supposed to be a coffee? Because I told it. I told it if I get these inputs, it's supposed to be coffee. Okay. Now what's happening is, this is where it's propagating that backwards. Right? I don't know if you guys missed that. 1 second. I missed that. Oh, man. I just can't forward this. I don't want to play this again.
We get to see it again.
Yeah, kind of, right?
You should have machine learning fix that video player. Instead of like write an algorithm to like play it, right? And then it'll just fix itself.
I know. Oh, I'll try it one more time. But basically what happens is, after the first pass, it's going to blank out the weights, right? And it's going to give you a new set of weights. Now it gets the new set of weights because it's learned that I need to fix my error. How much do I need to change my weights so that I can reduce my error? Right? So we saw this still here. I'm scared to pause it, okay? So, right? So it's gotten here. Okay. Now the weights are gone. Now it back propagates. See those new set of weights on top? That's what it's learned as the right weights, right? And it basically propagates in here. The reason is the weight propagation is from back to the front, because it starts at the error, and then at each layer it's able to calculate what the error in the previous layer is, right? And then what it does, it uses the same weights and runs the calculation again. Now it's running the calculation again. Okay, so now see, the nodes that it activates is different. I'm not saying it always will be different, but for this example, it's different, right? And then, so it's gotten the other two nodes active, right? And then what it finally does is, yes, it's gotten coffee, right? So this is just an illustration of what I was trying to explain.
Can I try to wrap this analogy in my mind, getting back to it, tell me if I'm completely off? So we're training this vending machine to give us drinks based off of the time of day. And in the beginning of the train, I'm saying I'm putting an input that it's nighttime, my mood, etc., right? And then I'm giving it, I want to drink a beer.
Yes.
And then it runs it through the neural network. And correct my terminology if I'm off. It runs it through the training, right? And if it comes up to a different beverage, it's going to retrain something just the weights. And then the end goal is for it to be predictive so that we can remove the inputs and then, it'll reach some API, figure out the time and dates or whatever, and then give you your drink without needing any humans. Is that right?
So your inputs don't change. So what you said is, so I'm just going to say morning, low energy. Let's just fix it to 2, okay? Morning, low energy. So morning, low energy, I've already told the system that I want coffee, right? The system has that information. It stored that information. Think of it as, or basically it can look at that output. For the same input, morning, what is the other one I said? Low energy, thank you. Morning, low energy, the system knows that I need coffee. Then what I do is I feed the same input, morning, low energy, I feed the system. The system says I want soda. Then the system compares the soda with the coffee. It compares the soda with the coffee, and now what it has got to do is, how do I make the soda coffee? How do I change my weights so that my output becomes coffee instead of soda?
Thank you so much.
Right? So how that is done is using back propagation, and it basically it does a thing with calculus where it's able to calculate the weights back and propagate it to the initial layers, right? But we don't have to get into that kind of a deal. But this is the overall picture. It does the comparison, it finds the error, and it tries to reduce the error. Now, this is a very simple analogy. What actually happens is you don't take one input like coffee, low mood, for example, and pass this. You pass a bunch of them. You pass thousands of them. So what it does is it looks at, let's say, 100 of them together, right? Calculates the average error, and then tries to adjust the weights based on the average. Because doing it one by one is going to take it forever, right? So it's just an optimized way of doing it, and it's better to do that way. Because the other thing we have to remember is you want your machine to generalize. You don't want it to be very, very specific. Because if you're very specific, what works for one input will not work for the other. So you want some kind of generalization in there. Anyway, that was just a side talk. Okay. Now, we spoke about everything has to be in number format, right? So for the example of weather, for example, you could have just done 0.2 or 0.3 or whatever. We were okay with having one numeral representation. But in the real world, it's not like that. Inputs are more nuanced. For example, the weather example that we spoke about, it could have 3 parameters or 3 dimensions. You could define weather as precipitation, temperature, and wind speed, for example. Another example is, okay, so there are 3 dimensions that define weather, for example, right? Similarly, and these dimensions, if you look at these dimensions in the real world, if you look at latitude, longitude, for example, right? The first one and the second one, they're very close to each other, just by looking at them. So latitude, longitude for the location is 2 dimensions. But if you look at these 2 dimensions, just by looking at them, you know that they are very close in space, right? The first one is Albany Airport, the second one is where we are right now, right? And if you look at the fourth one, the Eiffel Tower, you just by looking at them know that they are too far away from each other. Similarly, words have to have dimensions, multiple dimensions that define them. You cannot have a single number that tells you a word like cat or mat or something like that. You cannot have a single number representing words because language is very, very nuanced, right? A word like bank, for example, it can mean multiple things, right? And it could also have different dimensions to look at. You could be looking at gender, for example, plurality, for example, where it's a noun or a verb. So there are a lot of dimensions like that. In fact, GPT-3 uses 12,288 dimensions, right? And how they appear is like this, right? You just have a bunch of numbers separated by commas. They're called vectors, right? So the thing with this, when you encode words as numbers, you call them embeddings, or you make that into a vector. Vector is nothing but a list of numbers, right? Now, they have intelligence built into them, or in other words, they understand the context. What I mean by that is, if you were to embed the word king, and from king, if you were to minus the embedding for man, and add woman to it, the embedding you get would be similar to queen, right? Now, embedding has been in place for a long time. It's basically how to convert words into a bunch of numbers, right? This was I think, initially done by Google. There was this program called Word2Vec, which converted word to vectors, right? But the important thing to remember is embedding vectors have semantic or context knowledge. So, for example, if you take man out of king and add woman, that means the thing about king, right, it encompasses or it involves or it has gender and royalty dimensions. When you take out man from it, when you take out the gender and add the woman gender to it, you still have royalty left, but now you attach it to a woman, which makes it a queen, right? So it's difficult, first of all, for human beings to visualize anything over 3 dimensions. We are talking about 12,000 dimensions here. So this is the closest we can get to kind of imagine what is happening. We know this is true, right? We know this actually works, right? But the way to imagine is this, that you minus these two vectors, this is what is left of. So that is how we know that, for example, if you take Paris, subtract France from it and add Poland, you get Warsaw. That means the dimension that these vectors are, the 12,000 dimensions that each word has, it encompasses or it has dimensions for capitals, countries, geography, location, and all that. Right? Okay. Now we come to GPT, or Generative Pre-trained Transformer. So the base of most of the LLMs is the transformer architecture. So right now, the LLM we are going to discuss is just going to have text predicting text, text generating text, right? Now, that can be thought of as predicting the next word. Now, how predicting the next word makes sense to generating it is if you have this word, the weather outside is, and you pass it through GPT or a transformer, you get one of those options, right? So it's able to predict what the next word is. It gives you a percentage, right? So the weather outside is, let's say it's nice. Once you get the nice back, what you could do is you could add the nice and make that as a new input, right? So the weather outside is nice. So you first asked the weather outside is and you got nice as a result, right? You take nice, add it to the input, and you pass it again here, and it gives you the next word. And you keep repeating this, this is how it generates the next word. So that is how the next word generation alone helps you generate large amounts of text per se. So we will be trying to understand how this is happening or get an intuition around it.
I feel like that sort of explains sometimes why the text generated by AI can sometimes be really generic.
Yes, yes.
Because they're just choosing the most common.
Yeah, so I am not 100% sure they always choose the most common. You would think so, right? But if you have, this is something you can do on your own. You could actually download some models, look at the most common predictions, and write that program by yourself, right? I mean, it will not be perfect, but it gives you an intuition like you were saying.
Yeah. I mean, it's probably, like I think you're trying to say, it's not exactly like that, but I feel like that's sort of like a generic
Yes.
first-run approach.
Yes, yes. So like I said, right, nobody exactly knows how this is working. This is the intuition that we can gain from this. That yes, it is picking the most common word, like you said. Right? The next thing I want to focus on is attention. Right? Now attention, if you think of attention, what attention is, the same word bank in different contexts has different meanings. I walked into a bank, the park was located on the bank of the river, the pilot had to bang the plane. The same word, but based on the context, it has different meanings. Right? So if a language model were to take these three sentences, how would it embed bank? It cannot have the same embedding because then you would get weird results when you ask it to complete the second sentence, what happens after I'm on the bank of the lake? It's going to tell you something about a financial organization, right? But that doesn't happen, right? So there is context that has to be built into embeddings, right? We'll look into that. Okay. So what initially happens is when you let's say you're using GPT or a transformer to predict the next word, right? Or when you use that, right? Let's say the sentence that you given is this: the brown fox jumped over the lazy dog. Oh, this is a very famous word. There is this word called what is it? The quick brown fox jumped over the lazy dog. That is a sentence that has all the letters of the alphabet in it. I mean, I just picked it from there. But the first thing that happens when you feed a sentence into a transformer is it breaks it up into words. So you see those blocks, the brown fox, it's broken up into words. That's the first thing that happens. It's not perfectly words all the time. You can have, if you have commas and subwords and all that. But for the purpose of our understanding, just let's say it's going to break it into words. That process is called tokenization, break it into tokens, right? Then what it does is it assigns an embedding to each of those tokens. That is the second step, right? Now in this step, right, the initial...
Did you define embedding? I can't
Yeah, I did. Embedding is, this is the embedding. One second. Yeah, this is the embedding part, right? So basically embedding means a bunch of numbers. Bunch of numbers which have context understanding in them. They understand meaning of the words. So if you take two embeddings and minus them, like I was saying, king minus, maybe it's just the vocabulary. Vector, embedding, it's the same thing.
Okay, thank
Yeah.
you.
So if you minus king minus queen, you get the same as, sorry, king minus man plus woman will give you queen.
And it means subtracting the vector.
Yes, yes. Yeah, you can think of it like that. Right? Okay, so the initial embedding for that tokens, right? This is going to be the first one. Then what's going to happen is the third stage that I'm seeing where you're interacting with each other that is where the embeddings talk to each other. Meaning, the words talk to each other. So the brown fox, you have a brown fox, right? Now, fox by itself has an embedding. But if it's a brown fox, that embedding will change because there is context built into fox because it's brown versus if it was red. Right? And we need that because for intelligent interpretation of language, you need to understand context. Context of the sentence that the word is used in. Right? So that's what happens in attention. In attention, what happens is the vectors interact with each other, pass information back and forth so as to get context from each other. Right? That is what happens in a transformer. Now, in a transformer, it's just a bunch of numbers. What you're actually doing is you're just multiplying them, creating dot products. And that is why I showed that diagram at the beginning, the animation. Right? What happens there is you're just doing a bunch of matrix multiplications. That is how they interact. That is how they change the embeddings. Right? So what actually happens here is there is something called query. Right? Think of query as, so let's say we have this sentence. Snow wanted his sword back. Snow is Jon Snow from Game of Thrones, if nobody is a fan, but Snow wanted his sword back, for example, right? So what happens is, how does the embeddings influence each other is, think of it as, when you use his, right, you basically have what is called a query vector. A query vector is basically looking out for a bunch of characteristics. So you have query, you have key. Right? So query could be something where, for example, in Snow wanted his sword back, query could be like, I am looking for a noun describing a male person. Right? So the query for his could be looking at, I am looking for a male person. So I'm looking for a noun describing a male person. Right? And then what happens is, the key vector for Snow says, I am a noun describing a male person. So this is just a description of how they interact with each other. So you have a bunch of weights for each and every token that is in your sentence, right? You have a bunch of weights that is actually trying to do a matrix multiplication with the rest of the tokens in there and changing it. Now, how do you know that this token has to be changing this token and not something else? Is because that intelligence is built into the weights. Right? So just like we spoke about the intelligence built into the vending machine, which says that, hey, I have this set of weights that give me this prediction, this drink. Similarly, the weights that are used here have this intelligence built into the dimensions. I don't know if this is going above everybody, but this is one way to think about it. This is like, to understand context, think that attention is like a matchmaking service, right? You're looking for life partners, or a dating service, right? So what happens is, imagine each of those tokens are asking a question.